Alright, today we're going to be learning about how to find the theoretical probability of compound events. So go ahead and set up your notes for today. The title is Finding Theoretical Probabilities of Compound Events. And our essential question for today, how do I find the theoretical probability of compound events? This is digit 17.4. It's our very last lesson in this probabilities unit. So hit pause and set up your notes for today. Finding Theoretical Probabilities of Compound Events is the title. The EQ, how do I find the theoretical probability of compound events? Hit pause, and when you're ready to move on, hit play. Okay, now, finding theoretical probabilities when we're dealing with compound events, either independent or dependent events. Remember our formula for theoretical probability. It is the number of favorable outcomes over the number of possible outcomes. So first, if we are going to spin a spinner twice, we know this is independent events because the spinner is not going to change from the first spin to the second spin. You would list out the sample space to find the total number of outcomes. So red, blue, or green is the first option, and then from that, the second spin, red, blue, or green. So 3 times 3, there's going to be 9 possible outcomes, and then they want to know spinning the same color twice. We could get red and red, blue and blue, or green and green. There's 3 different ways that I could get the same color twice out of 9 possible outcomes. So that would simplify to be 1 over 3. Okay, looking at this table, they have given us the sample space of the combinations of the fish, star, apple, pea, and leaf cards. We're playing some kind of a game, I guess. All right, what is the probability of at least 1 apple? Well, first I need to know how many possible outcomes I have. And I see that this table is 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So 5 times 5 means I have 25 different combinations together. So that's going to be the bottom of my probability. How many of these have at least 1 A apple? I'm just going to circle them because it seems easiest to me. Looking for all the apples. I think I got them all. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 25 would have at least 1 apple. Then it says exactly 1 apple. So which one would I have to get rid of then? Can't have this guy if it has to be exactly 1 apple. That would be 8 out of 25. Alright, next, exactly 1 apple and 1 fish. So I want apple and fish, A and F. I have this one, and I have this one. So that is 2 out of 25. And then at least 1 apple or fish. So now I can have 1 apple or fish. So I'm going to have the 9 that I already had. Those all had apple. And then I'm going to add to that the fish, the F. So F, 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 and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 25. Alright, I'm going to flip to a second video just so we can finish this lesson real quick. There's not much more. Alright, last bit to cover on this compound events, counting outcomes stuff. Here we have an example. The tree diagram shows the possible outcomes of choosing 1 card and then setting it aside and choosing a second card. So is this independent or dependent? This is dependent. So looking at the tree diagram, what is the probability of at least 1 fish or 1 apple? So we would have all 4 of these combinations because that starts with fish. We would have all 4 of these combinations because that starts with apple. Then we would have the fish and apple, fish and apple, fish and apple from down here. So that is 4, 2, 4, 2, 2. We'll just add them all up to see what the total number of combinations would be. 4 plus 2 is 6, plus 4 is 10, plus 2 plus 2. That would be 14 different combinations having a fish or apple out of, we would have 1, 2, 3, 4 times 5 out of 20 different combinations we could make. So I would simplify that to be 7, it'll write 7 out of 10. Okay? Alright, it is your turn to pick a geography fair partner in country at random. Using and Greece, our favorite country. Okay, this will be the last example that we do. And this is going to be similar to one that you will have to do on digits. So please do this table with me. I know. Do this table with me in your notebook. It says a class ran 330 tiles of a two-step action. And the action is toss the coin and then spin the spinner. Complete the table. So if we have counted this many of each of the events, the experimental probability here is 45 out of 330. We could probably simplify that, but I'm not going to. 59 out of 330, 64 out of 330, 45 out of 330, 58 out of 330, and 59 out of 330. Okay? So that means that those are our experimental probabilities. Now, if we did the expected count, we would be thinking about what we would expect if we split up 330 divided by 1, 2, 3, 4, 5, 6. Okay? So if I divide 330 divided by 6, I would have expected each of these to give me 55. Right? 55. Which means that the theoretical probability would be 55 out of 330 or 1 out of 6. Okay? Now, let's answer our question. For which compound event is the count the closest to the expected event? So looking at our count, the actual what happened in the experiment, which of those is going to be closest to our expected count, 55? Let's see. 59, that is just 4 away from 55. This is bigger. This is bigger. This is bigger. Ooh, 58 is just 3 from 55, and this one's 4. So which one is going to be the closest? It's going to be this outcome, tails and blue. We ended up getting that the closest to the expected count of 55. We got that 58. Okay, so that was just 3 away from the expected count. That was the closest. All right, at this point, you should be ready to work on digits 18.3 and 18.4. If you need help, raise your hand.